understand this is very late. The first speaker is Qin Zhang, who is going to talk about distributive statistical estimation of matrix products with applications.
Thanks for staying until the last session. I know I think this session collides with the first session. I actually have a poster, but I cannot do this two tasks in parallel, so I think it's better to stay here. So my name is Qin Zhang, so I'm from Indiana University, Bloomington. So this is a joint work with David Wujuf from CMU. So we studied the following problem. We studied in a following model, the distributed model, where we have two parties, Alice and Bob. Alice has a piece of data, and Bob has a piece of data. Here you can think both of them have a matrix, and they want to compute some function on the product of these two matrices. Okay, so the goal is to minimize the total bits of communication and the number of runs. So the communication goes as follows. So Alice sends a message to Bob, and then Bob sends a message back to Alice, and so on. Okay, so the communication is simply the sum of the message lengths. Here, everything will be randomized, so it will be maximized over all choice of the inputs and the internal randomness of the algorithm. Okay, and we allow the protocol to fail with a small probability. So we consider the randomized case that we allow some failure probability. Okay, so we start a number of functions. The first is p-norms. So here they just want to compute the p-norm of the matrix C. Okay, so when p is equal to 0, this is just number of non-zero entries of C, and this corresponds to the size of set intersection join. So if you think each row of A is a set, and each column of B is a set, and they just want to. So this is just the number of pairs ij, such that the set IAI intersects with the set BJ. Okay? So I will give you an application of, if you're not familiar with set intersection join, I will give you an example in the next slide. So when P is equal to 1, this is simply a sum of the entries of the matrix C. Right? And this actually corresponds to the size of the natural join. Basically, we want to compute all tuples IKJ, such K is belong to the intersection of A and Bj. And I will also give you an example of this, more details about this statement. When P is equal to infinity, we simply want to compute the maximum entry of C. This is basically the most similar AI Pj pair. Okay, so this is application of example of set intersection join. So this is in the setting of job application. So we have a number of applicants. We have a number of openings. So each applicant has a set of skills. Each opening also have a set of skills that the opening require. So our goal is to find all the candidate applicant opening pair, so that the applicant has at least one skill that the opening needs. Okay. So this is basically, we want to compute all AI BJ pairs that intersect. All right, so this is the application of set intersection join. So to see like this, we call L1 norm of C corresponds to the size of natural join. So let's consider two tables. The first table has two attributes, UV, and the second table has two attributes, VW. We can convert these two tables to matrices. Okay, so here, like the 1, 2 basically corresponds to this 1 bit in this matrix, and 1, 4 is this bit, 2, 1 is this bit. So you can do the same thing for the second table. Okay, now, so just two tuple joins and produce a tuple 2, 1, 2. This corresponds to like this one multiplies this one, and they do increment the value of this cell, this 2 to C22 basically by 1. So if you sum up the value of all the entries of this cell of this matrix, basically that's the size of the natural join. Okay, good. Okay, so the second type of questions, some functions we consider as heavy hitters. So what we want to compute is want to find all the entries Cij that is above some threshold. So threshold is determined by phi times the p norm of C. And this problem is actually very difficult if we want a sharp threshold. So very often we allow some relaxation. Okay, so we actually compute so-called LP phi epsilon heavy hitter. Basically, we allow some error epsilon. We want to compute, so if the output has to include all the entries that is larger than the threshold, phi times the P norm of C, and do not contain any entries that is smaller than phi minus epsilon times the P norm of C. And for those entries in the middle, the decision can be arbitrary. So basically, we allow some epsilon slackness there. Okay, so this is the application of this is basically for similarity join. Basically, we want to compute all the entries or the pair of AI BJ that are similar to some extent to above some threshold. Okay, so I would like to say like those problems are actually studied. These are standard problem in the data string literature, but to our surprise, this has not been studied in the distributed computation setting, where two tables are stored in, let's say, two machines, and they want to compute those functions. Okay, so this is the motivation for this paper. Okay, so let me show you our main results. So for simplicity, let's assume the matrix is a square matrix. So, but our results also applies to all rectangle matrix. So for LP norm, so what we get is a two-round communication algorithm using n over epsilon bits, and we can approximate the P norm of C up to a 1 plus epsilon factor. So here tutor hides some log factors. Okay. So for p equal to 0, so this is a previous work of this. This is the only previous work of this for this problems. So for p equal to 0, the previous work needs this amount of communication. So basically, we shift the factor of epsilon upon the previous result. And the same paper actually showed the lower bound of n over epsilon 2 to the power 2 over 3. So this is a strange exponent, but. Also this previous paper shows if we restrict the communication to be one way, means we only allow Alice to send the message to Bob, and then Bob have to output the answer. Then there's a lower bound n over epsilon square. So our result actually shows separation between one-way communication and the multi-round communication. Okay, so this is for LP norm. And for L infinity, so this is for LP norm for P between 0 and 2. For L infinity, I think it's better to show these two results simultaneously. So basically, we get so we can approximate L infinity norm using n to the power 1.5 over epsilon bits. And if we allow a constant or any arbitrary approximation factor, then we replace this epsilon by kappa. For any kappa, so I think it's for any kappa. So, and we can show that those things are almost tight up to log factors. Okay. So if you want to approximate these things using a factor of 2, then you need the quadratic bits of communication. Okay. And all the above results are actually holds only for binary matrix, Boolean matrix. If we allow A and B to be, the alphabet size to be like a general sigma, then all these bounds will be n square over k square, kappa square, sorry, if we want to approximate, so this should, the F infinity norm of C up to a factor of kappa. So this is higher than the Boolean case. I should say like the lower bounds actually holds for any number of rounds, and upper bounds always constant the number of rounds. Okay, so this is for LP. And for heavy hitter, again, we consider two cases, like Boolean case and general case. So for Boolean case, we get a constant round and algorithm with this amount of communication. It's almost linear in n. Okay, and if it's general, then it's slightly larger. It's still constant round, but there's a factor of square root phi over epsilon. Still, some log factors are hidden in this tutor. Okay, So yeah, this is what I said, like all those results can be generalized to rectangle matrix. Then you have another parameter m, but the result will be modified a little bit, but a similar flavor. Okay, so that's our main results. Okay, good. So some previous work, as I mentioned, like this is the most relevant work. This is actually also our previous work 3 years ago in parts. So in that paper, we consider set intersection joint, disjointness joint, equality joint, some different type of joints. But the only overlap between this paper and the previous paper is this estimation of the L0 norm of the matrix C. Most of the results in the previous work are exact computation of C. It's not estimation. So this is the only overlap I just mentioned. There's a number of recent works look at how to solve linear algebra problems in a distributed setting, the same model. But the difference is that those works concerns the the estimation of C, which is A plus B, instead of like the product. It's a summation. Okay, so of course, like summation has no. I don't know like is there any like immediate application on joints. So for joints, you need the product. Right. So, and similar problems have been considered in the RAM model. There are a lot of works in the RAM model, but I think models are different. So we study in the district model, we concerns communication instead of a running time. Okay, our algorithm also have small running time, but that's the second consideration. Okay, so then the rest will be some technical details. If you have any questions, you can ask any time. So for those who are not very familiar with the sketching, streaming stuff, maybe you feel some notations are strange or something. So just let me know. Just interrupt me at any time. I try to go slowly. Okay. So just look at time. Okay. So the first task is to 1 plus epsilon approximate of the L0, the number of non-zero entries of C. So idea is very simple. So the naive approach is Alice can just sample a few rows of A and send to Bob, and then Bob uses those samples to compute a few rows, also sample rows of C, and then sum up the number of non-zero entries, then scale back. So that's the naive approach. This is basically what we did before, just one round. Okay, but the problem is that the rows of C might have very different number of the number of non-zero entries. Then the variance could be very large. So what we do is we try to reduce the variance by a more careful sampling scheme. So that's the main idea. So it's just once, I think that sentence captures the one main idea of our algorithm. So the high-level idea is more concretely. So what we do is we first perform a rough estimation of the number of non-zero entries of each row of C. Okay, then let's say like approximate it up to a constant factor, for example, not a 1 plus epsilon constant factor. And then we try to group those rows of C, partition the rows of C to a number of groups. Then the rows in the same group roughly have the same amount of number of non-zero entries. Okay, and then we sample rows in each group with different sample rate. Depends on basically the sample rate for a row in one particular group is proportional to the average non-zero entries of this group. Okay, and then we just Alice just sample those rows and send to Bob, and then Bob can estimate the sum up of the sample rows and then scale back. So this is the high-level idea. And next slide, this is just, this will probably belong to the same group. Okay, so this is just the implementation of this high-level idea I showed in the previous slides. So what we do is we use our previous algorithm to estimate basically each row of C up to a 1 plus beta approximation. So beta is a parameter. Beta is not epsilon. If it's epsilon, then we are done. Beta is larger than epsilon. Actually, we set beta to be this value. I will tell you why we set the beta to be square root of epsilon. Okay, and then we partition the rows, n rows of C according to the number of non-zero entries of each row. Basically, the else row, the else group contains all those rows with number of non-zero entries between 1 plus beta to the power L and 1 plus beta to the power L minus 1. Okay, and then we have the groups, and then we sample each rows in each group using probability PL. PL, so you can read PL in two parts. So this is like a fixed for all the groups, and this is basically the average number of non-zero entries of rows in this group. Okay, so this is just a normalizing factor. So this is like you can think this is like a global sampling rate. Okay, and this is something group dependent. And then Bob just compute sample the matrix, and then compute the number of non-zero entries of the sample matrix, then scale back, and that's all. Okay, so what's the communication? So the communication is dominated by the first step and the third step. This can be done by Bob only, I think. Yeah, so this is also by Bob only. So this step cost n over beta square communication. This is basically our previous result. And this step cost n times rho. Rho is the global sampling rate. Okay, and to balance those two things, this is why we set beta to be square root epsilon, and rho is 1 over epsilon. So kind of some balancing stuff, and then both of them will be become n over epsilon. Okay, and correctness can be proved by some sort of standard expectation variance and estimation, but because we sample more carefully, we have low variance, so that's why we get this improvement. Okay, but I will not show the technical details for this because this takes a few pages. Okay, so that's basically everything about 1 plus epsilon approximation of L0 norm, 0 norm of P, mean number of non-zero, 0 norm of C. Okay, so second result, this is the second thing I want to say, is a 2 plus epsilon approximation of L infinity. Okay, so the high-level idea is, again, by sampling. So again, the problem is try to compute the largest entry of this matrix C. Okay, so what we do is we want to, the idea is try to make C sparse. If C is very sparse, then, okay, then we can recover the cells of C exactly because it's very sparse. If it's dense, then it has a problem. So what we do is we try to subsample C, but we cannot subsample C because C is some product we don't know. Okay, so we instead sample A. Alice can sample A, and then so what we want to do is we try to subsample C via subsampling A to a level L, so that first the L1 node of CL is this like sampled matrix is as small as possible, but still the L infinity of CL is after proper scale back is still can approximate the L0 also L infinity node of C to a good to 1 plus epsilon factor. Okay, so this is the idea. I guess it's 5 minutes. So, okay, yeah. Okay, 3 minutes. Okay, so probably I will skip these things. Maybe I will. Yeah, let me explain this algorithm. Then I'll skip some of the analysis. So this is what we do. This is basically what I said. So first I subsample the matrix A. This can be done by Alice. Subsample matrix A to get a hierarchy of matrix A1, A2, A3. AL is just subsample each one in A with this probability, and then let L star to be the smallest L, so that the L1 norm of CL is less than gamma times n squared. Gamma is some, you can think some log factor. And then what we do is we focus on this level. Basically, we focus on this CL star. And then for each J, let Uj to be a number of ones in the J's column of A L star, and the Vj is the J's row of B. And then we look at these two values. If uj is less than vj, then Alice just sends the j-scalar of al star to Bob, and otherwise Bob sends the j-row of b to Alice. And then, based on this information, Alice and Bob can compute two matrices, CA and CB, and their sum is exactly equal to CL star. Okay? And then we just output the L infinity norm of CA and the max of L infinity norm of CA and the max of the L infinity norm of CB, and the profits go back by the sample rate. And we can show that this is a 2 plus epsilon approximation of the original C. Okay, so the sum analysis probably was, because of time, I will skip. But I think this line is simple because this basically we can show after subsampling this approximate the original L0 norm, so L infinity norm of C well to 1 plus epsilon factor, and we also have this. So the max of this 2 is a two approximation of the L infinity norm of C L star. And combining these two, we get 2 plus epsilon approximation. Okay, so I will skip the communication cost analysis. So just conclude what we have. So just recall like our main results. We get 1 plus epsilon approximation for LP norm for P from 0 to 2, and our communication cost for this is n over epsilon. And we got the algorithm for estimating the L infinity norm of C, and if the matrix is Boolean, then our communication is, I think I lost one over epsilon here, so it's n to the power 1.50 epsilon, and for general approximation, this is just replace this by kappa. Okay, sorry. And for heavy hitter, we get, so I didn't have time to talk about heavy hitter. So this is what we get for heavy hitter. And for general matrix, we get phi over epsilon times n. And for Boolean matrix, we get n plus phi over epsilon square. And there are a few open questions. First, I mean, we still have a gap between the upper bound and the lower bound for LP norm estimation. So the gap is like roughly 1 over epsilon to the power 1 over 3. And how to close this gap is an open question. And for this, for heavy hitters, we don't have any lower bounds. We don't know if those are tight or not. Okay, so that's conclude my talk. Thank you. Hi.
I don't know if this is working. Oh, it's working? Okay. So you didn't mention your LP estimation algorithm discussed for time, but do you do the same sampling thing where you
For LP?
Do you sample with like lever score probability?
So LP is
the LP estimation.
It's basically the same algorithm.
But you sample with respect with like the
it's to a power p, everything to a power p, p norm.
Okay.
So it's basically the same thing.
Okay. Out of curiosity, have you thought of trying to close the gap by multiplying by? Hello? Oh,
Yeah.
there we go. Okay.
Yeah.
Have you tried like trying to close that gap by multiplying by like a sketching matrix, one of these like a Johnson-Lindstrauss transform? Like if Alice multiplies on the left by some matrix, then this reduces the number of rows. Perhaps you need to sample.
Actually, you can think the hard case is when n is 1 over epsilon square.
I see.
So Johnson and Strauss will not give you anything.
Okay, I see. All right. Thank you.
Yeah, sure.
I have a quick one on
Sure.
Have you thought about the cases where there are more communication parties, like A times B times C times D?
Oh, so multi-party, like, yeah, this is a good question, like, especially like in the distributed computer model, like multi-party, right? So tables have stored in more than 2 machines. I don't think this will work, so I think it needs some new ideas. We thought about this, we thought about a particular type of join multi-way join, but yeah, the results not look good. So yeah, it's harder than this, because if you have multiple tables, sometimes the output will be 0, nothing, and you cannot detect it very efficiently. So that's a problem. Yeah.